We looked at going ahead and finding volumes using the disk method. And that's where the object is solid. But sometimes when you go ahead and revolve a rectangle, it's not right on the axis of revolution. And when you revolve that, it ends up really forming a washer. So it's like a disk with a hole in the middle of it. Well, we approximated the volumes before when it was solid with disks. We can do that also with washers. The only thing is, to figure out the volume of a washer, we don't need this inner hole. So we got to subtract that volume. So really, it's the area of the whole big disk, the outer part, which is your area of your circle, which is your pi, times your big radius, the outer radius, times your width. But then you got to subtract the inner circle, which we don't want to include. That's just like another disk that we got to get rid of, but it's still going to be pi, but we got to get rid of that radius squared, so pi times r squared times your width. For that inner one, that's what we're getting rid of, so that's why it's being subtracted. So when you have a washer, which is basically where you have a hole in the middle of your shape, you're going pi, your bounds, your outer radius squared minus your inner radius squared, and you're integrating with that with respect to dx. So if we take a look at this graph here, we want to go ahead and find the volume of our shape by taking the area bound by our square root of x, which is this top curve, and our x squared, which is this bottom curve, which is our parabola. They meet at 0 and they meet at 1. When you take that and revolve it around the x-axis, we end up getting this shape right here formed. We want to go ahead and then find our volume of this shape. It's kind of like a bowl here, where the outside's a nice curved parabola on the outside, and the inside we got this kind of curvy V. So it could be a bowl or a vase, something along that lines. So we have a hole on the inside, so we want to go ahead and use the idea of a washer. This is our washer method for when we're dealing with the horizontal axis of revolution. Our bounds for our integral, we know we're dealing with x's, so we got to look at where their x's start and stop for the shaded region, starting at 0, going over to 1. So our bounds are from 0 to 1. Then we need to go ahead and take a look at the outer radius. The outer radius would go from the farthest part away from your axis of revolution, which in this case is the function that's on top, minus our axis of revolution. So that's our outer radius, and that's what we're going to put right here. Our outer radius in this case is our square root of x function. And then that's got to be squared, minus, and then we need to do our inner radius. Our inner radius would go from the inside of our shaded region to our axis of revolution, and that's going to be our inner radius right here. For this particular problem, it's going to be from what's on top for our x squared right here, the curved one, minus our axis of revolution. So it's x squared minus 0. Then all we have to do is go ahead and just solve this. We can square each one of these parentheses, and then it's just normal integration, increasing our exponents by 1, plugging in 1, minus what we get when we plug in 0, and we get 3 pi over 10.